This is Giuseppe Macoretta from the Department of Civil and Industrial Engineering of the University of Pisa, and I'm going to talk about our work dealing with productivity-oriented process parameters effects on the fatigue strength of selective laser melted Inconel 718. The aim of our work is the assessment of the effect on the cyclic mechanical properties produced by selective laser melting process parameters that are devised to increase the system productivity. We will see the selection of the selective SLM process parameters, the effect on microstructural properties of the material, the effect that they produce on the high cycle fatigue behavior, and finally fractographic analysis in order to understand the region of fatigue crack concept. Which are the limits to the industrial spread of selective laser melting? This technology is well known to have the ability to produce complex shapes, to shorten the time between design and final product, to allow for huge product customization, to introduce important scrap reduction, waste reduction, and energy consumption reduction. But the spread of this technology is currently limited by poor cyclic mechanical properties, poor surface finish, particularly in this SBIT condition, but also lower productivity rate compared to traditional manufacturing processes. How can we cope with this lower productivity rate? In order of increasing costs, we can speed up the process by developing the specific process parameters that exploit the possibility introduced by new machines in order to speed up the process and increase the productivity rate. We can introduce multi-laser machines, or we can install additional machines in our manufacturing plant. In this work, we'll focus on the possibility to speed up the process by developing specific process parameters aimed to increase the productivity rate of the process. The adopted process parameters were selected on the base of an analytical model of the selective laser melting process. It's a simplified approach that is based on the Rosenthal solution of a moving point heat source, namely a point heat source that moves along a straight line with constant velocity. We focus on the steady state phenomenon, and we consider a semi-infinite solid with constant thermophysical properties. So we make some assumption to simplify the analysis of the process, but trying to keep only the information that we need to try to develop a feasible region of the process. This approach allows us to obtain the thermal field produced by a single laser can in terms of the dimension of the melt pool and prediction of the risk of lack of fusion or humping. The full model will be presented with its development and validation in a dedicated paper that currently is under submission. The process parameters were devised keeping fixed the layer thickness, in this case 60 microns, and so preserving the process resolution in the vertical directions. Were selected two sets of parameters, named A1 and A2, having different aspect ratios of the melt pool. These process parameters were compared in terms of productivity rate by evaluating the build time in the production of a simplified job formed by 20 specimens. Each specimen is a square section bar, 10 millimeters per 10 millimeters per 100 millimeters, and considering a recoating time of 4 seconds between each layer. If we compare the job build time between the standard process parameters for Inconel 718, here named baseline, also in the further slides, and the selected process parameters, we see that the selected process parameters introduce a strong job build time reduction, which is almost halved, both for the two possibilities of process parameters that here are investigated. It was used a standard Inconel 718 powder for selective laser melting, featuring a particle size distribution comprised between 13 and 53 microns. All the specimens were printed by using the Renishaw RENAM 500E printer that is installed at our university, and all the specimens were printed in vertical direction. 3 sets of process parameters were employed, so baseline, A1, A2. All the specimens were tested in the as-built condition, both for the surface condition but also about heat treatment. The heat treatment was absent. We test the specimen in the condition exactly after printing. The high cycle fatigue tests were carried out on standard cylindrical plane specimens in the stress ratio of 0, so repeated loading, with test frequency of 150 Hz. Metallographic investigations were carried out to analyze the material porosity, both sectioning our specimens in transversal and longitudinal directions. You can see on the left a picture that shows you with the 2 different colors the definition of transversal and longitudinal direction. Longitudinal direction is the direction that comprises the wheel direction, the Z direction. Here on the right part of the slide, you can see a comparison of 3 sections in longitudinal direction from baseline parameters, A1, A2 parameters. It's evident that while in the baseline condition the porosity is almost absent, we see only some small pores due to gas entrapped. When we move to productivity-oriented process parameters, the porosity increased. In the A1 is greater, in the A2 is still greater than the A1 condition. The same trend is confirmed by the measurement that we carried out on different sections of 3 specimens per each set of process parameters. We see that while in the baseline condition the material density is almost 100%, both in longitudinal and transversal direction, when we increase the productivity rate, the material density tends to decrease until 99.5 for the A2 parameters in longitudinal direction. A similar trend is visible also if we consider the maximum area of the defect that we can find in both the 2 sections. Even if we can see that the A1 process parameter set has still a higher density, but tend to introduce some bigger defects compared to A2 set. The A2 sets produce a wider diffuse porosity, but with small pores compared to the A1 set. But if we move to analyze the fatigue behavior, we see that in spite of the increase in porosity, the fatigue response of the specimen produced by using the productivity-oriented process parameters, it's almost coincident with the specimen produced with the baseline parameters. In particular, for the A2 parameters, we see that the data are almost coincident. We represent the 3 datasets on the same figure, and we introduce the standard statistical analysis approach conventionally used in the high cycle fatigue test analysis. We see that the effect of the A1 and A2 process parameters is only to move towards the bottom, the curve. The 3 curves are almost parallel, with a fatigue strength reduction that is greater for A1 set compared to A2. The 3 data sets are so near that the confidence bands are almost overlapping, in particular for baseline and for A2 that are, as I said before, resulted in a fatigue behavior that is almost coincident. To summarize, if we consider only the reduction in the stress range at 1 million cycles, we saw that compared to the baseline in the A1 process parameter set, we have a reduction of 40%, while in the ATU process parameter set, we have a reduction of only 7%. For all the tested specimens, the fracture surface was analyzed by using stereo microscope and scanning electron microscope in order to understand where is located the fatigue crack onset and if near to it are present some pore or defect that can have affected significantly the fracture nucleation in this fatigue life. For all the tested specimens, the fatigue crack onset resulted to be located in proximity to the specimen surface. And as you can see from the three pictures taken by scanning electron microscope that are represented here in the bottom of the slide, and with the fatigue crack onset highlighted by the red circle, in proximity to it are not present significant pores or defects that can have affected the fatigue life. But we can see that near on the surface for each crack nucleation are present some superficial defects that are defects that almost tend to the surface roughness of the specimen that seems to play the most important role in affecting the fatigue crack nucleation induced the fatigue life of the specimens for the three sets. To conclude, we can see that the proposed productivity-oriented process parameters result not to affect significantly the material fatigue strength, which, if we consider the strength at 1 million cycles, was reduced by only 7%, while the productivity rate is almost doubled. This is the case of the ATU process parameter set. We saw that the productivity-oriented process parameters produce a significant increase in material porosity, increasing both the porosity and reducing the material density, but also increasing the dimension of the single pore. But in the tested conditions, we saw an almost null effect on the high cycle fatigue behavior of our specimens. Future developments will deal with the better investigation of the surface roughness, its characterization, and also further investigation on fractographic analysis of our specimens. Thanks for the attention. If you have any questions, please email me to the address that you see on the slide. Thanks again.